This is a continuation on the talk on dynamic programming. So last time we went over the Fibonacci sequence problem, and we showed how you can use a table to cache the results that you've already computed, and then you can use those intermediate results to as the sub problem solutions that will be useful for the larger problems. And that speeds up things by a lot. Actually, last time I didn't show you how dramatic a speed up it can be, so I will do that now. So if we run this Fibonacci program, there it returned with a value pretty quickly. But we were only doing, well, okay. Actually, let me show the slow version first, because this is the fast version. So I'll comment out the part where it looks up that table and inserts into that table. So this should be the slow version now. Except for that. 1 second. Let me do this. So the table only has the entries for 1 and 2. So it's going to look up the table for those so that it at least stops. That there's at least a terminating condition to the recursion. Okay, so if you do this for a large-ish number, it's actually going to take a while for the program to finish. I don't know if I want to wait that long. Let me do a smaller number. Let's do 50. Well, okay. I don't know if I want to keep waiting, but as you can see, it takes a while just to calculate the 50th Fibonacci number. If we, on the other hand, turned on the cache feature, then we get the result instantaneously. And that's how big a difference it can make. And the reason it's taking so long, again, as we saw last time, is we're doing a lot of redundant calculations that were already done before. So the caching makes this speed up possible. One thing I also sort of hand waved last time a little bit, but I'm gonna make it explicit this time, is alternatively you could do the bottom-up approach. For every given dynamic programming problem, you can do it the recursive way with caching, but you can also do the bottom-up way. Most of them you can. And for the Fibonacci problem, you would just make a table that's the size, or make an array, I should say, that's the size of the like if you're getting the nth number in the sequence, then you would make an array of size n, and you just fill up each number in the sequence and starting from the bottom. So if I run this program, you'll see how it works. It actually calculates every number inside the sequence and puts it in an array, basically. And then the result is just the last item in the array. So today's problem we're going to deal with is the longest common subsequence. And this is an interesting problem, and it's harder than the first one, than the Fibonacci or the coin problem that we looked at, because if we do it this bottom-up way with an array, we're gonna end up with a 2-dimensional array, and I'll show you what that looks like. So let me explain this problem first. So this is the longest common subsequence problem. It's a classic problem for teaching the dynamic programming concept. And there's this concept of subsequence. Let me explain that first. So the example given is ACE is a subsequence of ABCDE. And the reason ACE is a subsequence of ABCDE is because you can get to ACE from ABCDE by deleting characters from ABCDE. So I can delete B and I can delete E, and the result is ACE. Thus, ACE is a subsequence of ABCDE. Another way of saying that is the string ACE is a string where each character belongs in the second string ABCDE, and each character is like an increasing order of the order that is within the second string. So the C in the first string has to come after A in the second string, and the E in the first string has to come after C in the second string. Okay, so that's what a subsequence is. And this problem is like, given two strings, I want you to return the length of their longest common subsequence. Well, what does that mean? Well, in this case, ACE is a perfect, like, it's just a subsequence of A, B, C, D, E. But what if the first string had some letters that are not in the second string? Like, I don't know. I'll add a B. So I'll add a B. A B is actually in here. So that's interesting. I'll add something else. I'll add Y. So if I had two strings like this, I'll add another letter, maybe M here. Then the longest common subsequence between them is still ACE. Trimming off this guy and trimming off these two guys. Does that make sense so far?
Yeah.
Any questions? Okay. So how would we do this? Any intuitions? Anybody want to throw at me? Well, yeah.
I mean, this is thinking stream of consciousness more than anything.
Yeah.
But we know that if it's a subsequence, that we have to find A first, and then we look to see if there's the second part of the sequence, I think. So for example, we know that A, B, C, D, E is longer, right? So we probably want to first check for A and then see if there's an AC. Like, now that I can realize why this is going to take forever, so it's probably not the right solution. You look for A,
but
then,
no,
then keep going in the sequence until we hit a C. And if we don't hit a C, then we can start with the next letter in the first sequence, you know, and then just find the longest version starting with each letter. Does that make sense?
Longer, like start, like, oh, you're saying like try to, let me
figure out what the longest one is. So if we're starting with A, we're looking for A in the second sequence.
You're kind of saying, I think you're kind of saying I think what you might be leading us to is like try to match A, C, E, maybe. Here, no. Try. Oh, if you see, yeah, look for an A first. Like you're like, or look for, you have an ace. Yeah. So and you have a position at the A of ace. So you're gonna look for the first A. And then if you look for the first A, if you found the A, which we did here, then you're gonna advance this pointer to C, right?
Right.
And then you're gonna start at the letter after this guy's A, which
Exactly.
is B. You're starting here and you're going to look for CE, right? Or,
Well,
or you're going to look for C, right? You're going to look for the first C after that, and then you're going to find it here, and then you're like, I have another match. So and all the while you're accumulating how many letters you've gotten. So at first it was 1, and then you got 2, and then now that you found C, you're gonna up the pointer here. And then you're gonna again look for, starting at D, you're gonna look for the E, you're gonna find it here, and then you're gonna say, hey, I found 3.
Exactly. I mean, there's other like things you can do to return early, because obviously if it's the length of the sequence, like there's things, but I don't think that really matters for big O notation. But then, like, let's say that these were bigger ones, and you might have to go through again and say, like, hey, were there any C's before I got to the first pointer? And if there were, theoretically, there could be a longer sequence before, you get to your first pointer.
Yeah, so you're saying this algorithm may not necessarily yield the optimal solution, like the longest one.
Well, I assume that you're going to tell me what the optimal solution is. I mean, it's going to yield the longest one, because if we start from the beginning, so if we're doing ACE, we found what the longest substring is starting with A. So then I want to move on to say C, and really I only have to start before the A sequence, because everything else is going to do it. So like, let's say that there were letters before the A. I could actually stop once I hit A and then, add the rest theoretically, because, well, I have to think about that. But the point is I can go through each letter and see if there is a longer subsequence based off of where my pointer is on the first one. Yeah.
Hold on. I think you have a point there, but I'm not totally catching it. So you're saying,
So like, pretend before the A in the longer substring, there is like CE. Yeah, so let's pretend it's CE, A, B, C, D, E, and then we're looking for ACE.
okay.
Theoretically, I found that ACE is already a substring, but let's pretend I don't just return, because I know that that's the longest possible substring.
No, actually,
I would check C. So now I would be like, okay, well, what's the longest substring if I start with C? And so the longest substring if I start with C is going to be 2, even though it happened there.
Yeah.
Yeah, exactly.
What if it was CEABC, and then you went for ACE?
Right. So then I would see that
and then you would, if you found A, then that skips the CE, and then we lost these 2 letters here.
So then I would have to check starting from the C to see, like, okay, what is the longest substring starting with C, and that would be CE, which is 2.
So what you're saying, yes, yeah, that's a good point. Yeah, and that's sort of the case that we're trying to suss out. Like, if you, it's not good enough to just look for A, because that could have skipped some valuable letters. So so we want to start at this, maybe we should like start from the A for the first go, and then start from the C on the second go, and start from the E in the third go, etc. Yeah,
Exactly.
that's what you're saying.
Yeah, that's like my top of the head stream of consciousness.
Yes, that's actually very good. And that's a valid solution, but it's not the fastest solution. So, and your solution actually works, but it's gonna have a big O of n squared, I believe, or wait, n, where n is the length of times m, I believe, where m is that string and n is that string, because you're like you're going through this string essentially twice, or half of twice. It's a triangle kind of thing. So that's a good intuition. But the way we can do better than that is we say, hey, we're gonna scan from the left to the right, character by character. Let's put like another letter here. Is that a word? So we're gonna, well, let's do a simple case first. Go back to the simple case first. So we're gonna have a pointer that's keeping track of where we're looking on each string, and then we're gonna compare the character at the pointers, and if it matches, then we can actually safely move the pointer over for both of them. We can just simply like, hey, the A matches, we can +1 on our longest common subsequence length that we have so far. And then we can break it into a subproblem where we're doing the same thing to the substrings.
I see.
And that always works because even if there was another A later, that doesn't add to the total score. Like we could, if another A like here comes up, and yeah, we lost the opportunity to match this A with that A, but it doesn't subtract from our score. We still get 1, even if you match this A versus this A. It doesn't matter, right? So
we put a C. I mean, I don't know what order you wanted to do this, but if we did like C, A, B, C, D, E, like how we would account for, you know,
yep.
that.
Yeah, let's do that case now. C, A, B, Okay, so the question is like if the letters under the cursor are not the same, then what do we do? Well, we can't sort of advance both of the pointers, or we don't want to, like last time, because, well, we actually can't. It would be incorrect because that is advancing the pointer kind of mean you've found a match for it. And so we don't want to advance, but we want to shift over one of them. Like if we shift over this one, then we will find the match on the next turn. The problem is, what if that skips over something useful? Because maybe it's C, A, B, C, E, D versus A, C, A. I don't know. like there's something useful here, and we're comparing these, and if we advance this one, then we will miss out on the opportunity to match this C over here. Whereas in this scenario, it's good to skip this one. So in the top scenario, the desired step is to skip over the top string. Whereas for the bottom one, the better solution is to skip the bottom string. Does that make sense? Because if we skip over this A on the bottom, then we get to match this cab.
Mm-hmm. Yeah, so that, I think that's the question. So how do we do that without, you know, iterating over again and getting to the O and I forgot what it was. O and 2
Yeah.
or...
Yeah, so what we want to do is we're going to try both possibilities. We're going to try both advancing the pointer in string 1, and we're also going to try advancing the pointer in string 2 as well. So in the other words, if we have like a situation where we have a letter and we can't see what letters are coming after the current letter, the nature of the algorithm, and if the letters are not matching, what we're going to do is we're going to try matching the rest of the letters in string 1 with the string, the current state of the string 2 as is. And we're also going to try matching the current state of string 1 as it is with the rest of the letters in string 2. We're gonna try the algorithm on that and that recursively, and we're gonna see which one does better, and we're gonna pick the one that's better, that returns the longer sequence.
Still there?
Yeah.
Okay.
I don't know if I explained that nicely, but let's try this. Let's try this. I'm actually gonna, okay. I'm gonna call this longest common sequence. Okay, so basically we're gonna, I'll call this LCS. So we're gonna do ABCD versus ACE. And it's just gonna print a number. That's all it's gonna do. Yeah, and in this case, the number should be 3 because it's ACE. What's another example? We said something like lazy or something, and that should also be ACE. Another example we talked about was like, what if there's a C in front? Then we should also get ACE. I'll just start with those, and we'll come up with counter examples. I have S1 and S2. Okay, so let's check for the length first. So if the length is 0 for either of them, then we'll just return 0. So now we start this the algorithm where we have this cursor, and the cursor is just pointing. We're just gonna use a substring to peel off letters from each string when we recursively call the function again. So here we're just gonna look at the first letter because the first letter effectively is the cursor. Or maybe we want to. Or maybe we want to do it with the cursor, like I and J, like that. Which one do you prefer? Do you prefer have like an index cursor, or just imply that the beginning of the string, the first character is the cursor, and we'll just trim away at the string?
Yeah, we can just trim away the string. That's fine.
Okay. Okay, so in that case, we're gonna say, hey, if the first letter is the same, in both of the strings are the same, we're gonna trim away one letter from both of them. So the answer is gonna be, we got 1 because this match counts for 1. And then we'll recursively call ourselves with, in Python, the way to trim away a letter, do it like a substring. In JavaScript, it would be substring 1, like that. But in Python, there's a slicing operator that looks like 1 colon. So that's how we trim away the first string. What's that? Correct. Huh? Okay. All right. So now, so that's the case 1. That else what we want to do, as I said, is we want to try 2 cases. The case 1 is we want to trim away 1 letter from the first string, but keep the second string intact, and then vice versa. And we want the best of those. So answer 1 maybe. But we're not going to add 1 because we don't have a new match. So we can't add 1 to the length of the longest common subsequence in this case. So case 1 or answer 1 is we trim away 1 letter from the first string, but we keep the second string intact. And then case 2 is we keep the first string intact, but trim away a letter for the second string. And we're going to take the max of that. Whichever one is the better one, we'll say that's the one. And that's the answer. We'll return the answer. Okay, let's see if this works. 3, 3, and 3. I guess that's right. Oh, one thing. Let's just do one of them. I'm going to use my debugger to help us visualize what's happening. Okay. I think I can say C calls. Okay. Let's see this like this. Okay. So what happened? Let's see if we can piece back together what happened. So initially we called the LCS function on these 2 strings. The result was 3, but that was based on these subcalculations over here. Because in order to calculate the answer for these guys, we have to calculate the answer for these guys. So in this case, we trimmed off the A from both of them. So we're comparing BCDE to CE as a subcalculation. Okay, and then in order to calculate the number for these 2 substrings, we actually had to try 2 cases. This case and this case. So like the first case trimming off this B, and then the second case trimming off this E here. I mean this C here. And let's follow just one of these paths down. And then we go further down, and then because this C here actually matched this C, and for that reason we got another point. We got another count in the length count, and then we can trim off the C. And so we're comparing the DE versus the D, and then we have 2 cases to compare. The case of taking away the D, which gets us E versus E, and that eventually gets us another point. So this point gets added to this point, gets added to this point, we get 3. That is how the algorithm works. Does that make sense? Overall?
Yeah, I think so.
Yeah, I hope that, like, yeah, it's a little complex, but that's what it's doing. But in this case also, since we're doing dynamic programming, we might be doing some redundant work. Let me see. Yeah, like this is redundant work for we're comparing the 2 E's here. We're comparing DE and E in 2 separate cases here. So there's definitely some redundant work. And because of that.
Yes. Refactor that though. Can we throw this into Elite Code and just make sure it passes all the test cases?
Oh, it won't, because this is going to be extremely slow for multiple reasons. But let's do it. I'll just. Oops. I think it'll pass the first case, probably. There, it passed the first case. And then if I try to submit through all of the cases, it's gonna exceed the time limit, I'm pretty sure.
Yeah, so that's the fourth one.
And that's
If you
because
can refresh it too. If we can see what the fourth test case or one of the test cases is with the time limit exceeded. So it's not even that long. it looks
yeah,
like.
this one is not even that long, but I mean, we could or we could put that in
So
here.
I'm worried about the one that says wrong answer. So like the time limit exceeded makes sense for refactoring, but can we check in on also the wrong answer?
It's not a wrong answer. It is the time limit exceeded on this input, like while it was performing this input, because it says time limit exceeded. So it was already, oh my God, that's embarrassing, that it was already exceeded to the time limit on a very, very small input. So let me try running that locally.
Okay.
Oh wow, it does take a long time. I wonder why. But, like yeah, okay. I'm gonna do the call stack thing on it, and oh, even that is taking too long. Okay. So there's probably something about this string that has a lot of, so that's a time when you should think to yourself, maybe some caching would be helpful here. So again, we're gonna apply the dynamic programming principle of when there's a lot of redundant computation going on, we're gonna cache things. So
Can I ask
yeah.
you a question about
Yeah.
Elite Code? Go back to it.
Back to here.
Yeah, the actual thing. So like I see the ones that say time limit exceeded, but then there's the one at the bottom that says wrong answer. You're saying
Oh,
that
sorry. This is other submissions that I've done in the past.
oh, okay.
Yeah.
So it's not like you can see the test cases.
Yeah, the only one we've done in this session is this one.
Got it. Okay.
Sorry, but yeah, that's a yesterday. So let's do make a table, and then we're gonna jam the strings together into a unique key into the table. And then when we get an answer, we'll stick in the table and we'll look it up if there's a match. Okay, so in order to do this though, I want one new table instance to be created for each call of the function. Hello?
I think you might have cut out for a second there.
Yeah, cut out for a moment. Okay. I hope I'm back. Okay, so I'm gonna continue. So I'm adding this table parameter. I have to make sure I remember to pass it to all the recursive calls to myself. And now I'm gonna do the same thing that I basically did for the Fibonacci example, which is I'm gonna look up the table. Maybe not for, maybe right after this check here. I'm gonna look up the table by the key. I'm gonna compute the key, which is just, string 1 plus a separator plus string 2. That's the key. Although I have to mention, this is probably still going to be too slow, but for a different reason. So I'm going to say if the key is in the table, if we have an entry in the table by that key, we're just returning the cached value. And down here, if we've gone on and calculated the answer, going to enter it into the table. Okay. So let's try this. And now it actually returns in a fast manner. Okay, let's try this in the lead code. See if it will accept our answer. Oh, I forgot to pass in a table. Okay, so that works for this example. If I try to submit it, it's probably still gonna time out. Yeah, it still times out for. It won't show me this. There. It still times out for extremely long example. And the reason it times out this time is because each time we create a substring, it makes a copy of a really, really long substring. So the more times we do that, the more memory we consume on the system. And because it's a really long string to begin with, we're ending up creating like many, many copies of very long strings still. So a better way to do this, or a way to do this that actually passes the time limit, that finishes before the time limit, is actually to do what do it with the indexes. Instead of trim away at the strings, we do it with the indexes. So let's go ahead and do that. So we have to adapt these to the index. So we're never gonna trim away at these strings anymore, first of all. So we're just gonna pass in string 1 and string 2. And then for the first,
Doing the strings and then the indexes. I thought the functions doing indexes and then strings.
yep, exactly. So whereas before we passed in 2 strings, now we're gonna pass in 2 indexes and then 2 strings, and the strings we're never gonna change them. Yeah, so we're gonna have to modify these guys here. So if we want to trim away one character of a string, what we're in fact saying is we want to move the cursor by 1. So what we want to do is here, I'm gonna like the next version of I want it to be I plus 1, and the same with J. I want it to be J plus 1, and also, you know, we want to, when we call this, like later on when we go back here, we call this, we're gonna want to pass in 0 and 0 for the indexes. And also the length check, we have to convert it to a index check now. So index would be like if index is greater or equal to the length of the string, basically, then we're at the end of the string. Yeah. And then we're gonna return 0. And then here, instead of looking up index 0, we would look up index I and index j. And then again here, we're going to do I plus 1. Here, no change means we just pass j over without change. And here we pass I over without change. And then also, instead of using the strings as the keys, this was probably a thing that was killing us over here. Like we're gonna concatenate these 2 extremely long strings into this extremely long key and use that in the table. Now we're just gonna use the indexes as the key. And in Python, you can actually do this, which is called a tuple. This is a tuple of 2 numbers, and you can actually use that as a key into a table. Oh, it should be I and J. And you can use that as an index into the table. And let's attempt this. Okay, the first one works. Let's see if it passes all of them. Okay, it does pass all of them. Okay. Do any questions at this point? So this is similar to our Fibonacci solution where we use the table, basically. But we had more cases to consider in this problem. Okay, I do want to go over the bottom-up approach as well. This actually gets kind of interesting. So the bottom-up approach for this example can actually be visualized as a two-dimensional table. And so let's say our string was, what was our string? Okay. What we're gonna do is, so this is a grid. So we're gonna actually use a cell in the grid to represent what's the longest common subsequence of between the string starting at this position versus starting at this position. So the number in this cell should be what's the longest common subsequence between E and E. And the answer to that is 1 because E matches E. And then in this cell, we're asking what's the longest common subsequence between DE and E? And the answer to that is 1. Okay, and then these are all going to be 1 because I know that because none of these match E. It doesn't even matter if they match E or not. Actually, we already matched the E, so that's gone. You can't match more than one E if you only have one E on the other side. So, and then these are going to be 1. Okay. Now we're going to fill in this square. This square is, hey, what's the longest common subsequence between DE and CE? And the answer to that again is 1. But the way we know it's 1, the calculation we do to get 1 is we actually look at this value and look at this value, and we get the larger of the two. Because like if earlier on we got more scores up until this point, then that's the one we should pick. So here though is still 1, but here the C's are matching, so we get another score. So, and when you get a match, what you do is you add 1, but what do you add 1 to? You add 1 to the one that's diagonal from you, and that's that one, because you're gonna consume a letter, and then after you consume this letter C, because here you're matching between CDE and CE, and after you consume the C on both sides, you're gonna end up with DE versus E. So you want the answer for DE versus E, and that's this guy. So what we want to fill in here is 1 plus this one, which is 2. And here we're going to have 2 because we want a max between this guy and this guy. So we have 2. And here again, we have 2. And here D and A don't match. So we want the max between this and this. And that's 1. This is the max between this, and that's actually 2. And here we want the max between here, and that's both of them are 2. So this is 2, and this A matches. So we get 1 more point, and we get 1 added to this guy. That's 3. Any questions? Okay, so this is what we're gonna, this is the algorithm we're gonna write. And it's actually equivalent to this algorithm that we wrote recursively. It's an equivalent algorithm, except we're gonna do it in the bottom up way. And to make life a little bit easier for us, we're gonna add an extra row and an extra column and fill in with zeros over here, so that we don't have to do boundary checking. I'm just doing this so that the code will be much simpler to write. Although you don't necessarily have to do that. You can do boundary checking instead. Okay, so let's do it. So I'm gonna comment out the function we had, write a new version of this function, but it's gonna be bottom up. Or maybe I leave this one and call this bottom up. Okay. Now I'll test this function. Okay, so the first thing we're going to do is we want to make a table of the appropriate size. I think I'm going to go for I in range of length of string 1 plus 1. Plus 1 because we want that extra row for those zeros. And then I'm going to append a row to the table for each character in string 1 plus 1. And we're going to say in Python, there's this shorthand for you can multiply arrays to make a longer array. So I can say an array with a 0 in it, multiply that 5 times, and we'll get an array that has 5 zeros in it, like that. So I'm going to use this shorthand here to make an array of the appropriate length. And the length we want is the length of S2 plus 1. Okay, so we're going to end up with this table. I'll print out the table. Let's run that to see it. Okay, there's our table. It's nested. Each row has 4 letters. That's the length of A's plus 1. And it's got 6 rows, which that's the length of A, B, C, D, E plus 1. Okay, now we're gonna go in and we're gonna do 2 nested classical for loops, except Python doesn't have classical for loops. I'm gonna do it with a while loop, the old school way. And I'm gonna actually start at the end. But I'm gonna start from the right side of the table. So I'm gonna count in reverse. Basically, I'm gonna do I and subtract 1 from I on each turn. And I'm gonna do the same thing for J. I'm gonna start at the bottom and then work my way up. Okay, so those are our 2 nested loops. And we're actually going to do the exact same logic as we did over here, which is that, so if the letters at each cursor are the same, then we're going to come up with, we're going to add 1 to the count. And to which count? To to the cell that's directly diagonal to us, which is going to be in, so answer is 1 plus the answer that's diagonal from us, which is going to be 1 I plus 1 and I plus j. And here is why I put in that extra column and row of zeros. That way this will already have a value in it, which is 0 the first time I go through and do this. So if I was like the bottom corner of the table, like if initially I is going to be here and it's going to go diagonal, and I put a 0 here so that it will be able to get it. And then else, if we did not have a match, then what we're going to do, we want to plug the answer into the current location in the table. So it goes into here. We're sticking the answer into the cache. And then, yeah, otherwise, we get our answer via the max of table I plus 1. We advance the I pointer in one case, and then we advance the j pointer in the other case. And then we pick the better of the bigger of the two. And that's our answer. And now we're going to stick it into our table. Okay. And at the end of all of this, let's see what the table looks like. This should be plus 1.
I plus 1 by j bias 1.
Yeah, that should be j. Okay, that's what our table looks like. Let me print the table a little bit better. Okay, that's our table. So if I read that correctly, well, it's the same numbers as what we did by hand, just flipped. This 1 1 1, like this 3 is, yeah, it's the exact same table. It just rotated. So we're getting the correct answer, and the final answer we want to return is just the number in the top left corner, which is index 0 0. So 3. All right, any questions about this algorithm? Like, does it intuitively make sense? I'm going to plug this in, see if it checks out. Okay, that works. I'm going to submit it to all of them. And it worked. It actually did better than the recursive one with caching in terms of both runtime and memory usage. Why would that be?
That was going to be my question. So let's see. Well, it goes through. I mean, it's basically going to go through each. It's the length of input A times the length of input B, which is what is that in O notation? Is that N?
The length of input A plus length of input B, it will N plus M.
Input B, right?
Yeah.
Yeah, so that's N. And then for the other one, it is gonna be,
M? Or which thing are you trying to describe? Like you're trying to say the big O of something. The big O of what?
of each of these. So they're different, right? Like clearly the runtime and memory is very different in both of these solutions. So I was trying to calculate, well, what is the big N? You know,
The big O.
Yeah. Sorry.
As I understand it, the big O should be identical for both of these algorithms. So the reason that the actual performance is different, I think is something else. It's not that their sort of algorithmic complexity is different. It's more like dependent on something that's happening, the way that Python is performing the things. And my suspicion is I don't have a clear answer. Like if I dug into it, like looked into the performance of it, I can probably get a clear answer, but I have a guess. One guess is the bottom up one does not call functions. There's no function call in here. It's just one function with a couple of nested loops. And so it doesn't have the overhead of calling functions. And calling functions actually has a can be significant overhead if you do it a lot, which you are when you're doing a lot of recursive calls. So because every time you call a function, there's a stack. You have to remember. First of all, you have the local variables. Like you're calling this function. I'll just the language has to remember you're inside of this function call, and then if this function call calls another function, or not another function, calls itself, but with different parameters, it has to remember that so that when this function exits, it comes back to this function with the state of this one intact still. So every time you make a function call, this stack grows taller.
See, and that's all memory.
And that takes memory. This is using memory to do all of these things, and each frame inside the stack has to remember some local variables in there. Like in our case, it was like, well, these are the local variables. This is a local variable, and this is a local variable. So each frame has these things to remember within it, and then so this can grow tall and then come back down again, grow tall, come back down again, etc. Although because we have this caching, it doesn't go too crazy, I don't think, but it probably go really tall and then come all the way back down. But probably go do something like that. Whereas
comparing it, like here, there's always just one I and one J at a time. So it's not going to be consuming tons of memory in order to, the way that we're moving those pointers is that it's really kind of replacing in memory those things. So you'll never be stacking, as you did in that diagram. And then the other thing is, and then as far as runtime, I guess, just not having, I guess this is just a more efficient way of running Python. I mean, the memory part is easier to visualize, and then the runtime, I think, is a little harder without knowing the real ins and outs, but it's not like one is taking forever and the other one isn't, so.
No, well, the calling of the function has implications for the runtime as well. It takes time to set that stuff up and then tear that stuff down, right? Yeah, okay. Yeah, we're at time, so I won't dwell on it longer. So I'll close it here unless you have a last question, unless someone has a last question. Okay, well, thanks everyone for your attention.